started, and in this talk, I'm gonna give a presentation on a matrix completion problem with the graph side information like the Facebook social graph. And actually, in this problem context where there's a side information in doing the matrix completion, one natural question that one can ask is how much such side information can help doing matrix completion. So in this work, actually, we could answer that question by quantifying the gain of using side information. So in this talk, I'm going to present the result. Okay, this is joint work with my former student Kwang-jun and postdoc Changho and my collaborator Hyun-sung. Okay, so the recommender system is a problem context of this work. And as we all know, the recommender system is very popular. It comes in many applications, right? And also, there's a very standard technique used for operating the recommender system. That is a matrix completion. So the idea is very simple. We use the available rating to infer the missing entry. And we use that to recommend some item potentially preferable to some user, right? So this is how it works in operating the system, right? But here, there's some challenge in operating the system. The challenge is that sometimes we may have a very few number of ratings. So in that case, actually, it's not that easy to infer the missing entry, right? And in fact, in practice, that kind of challenge arises in the form of so-called the cold start problem. So here, the cold start problem is the problem that occurs when we have a new user or the new item like this. So in this case, definitely it's not that easy to infer the missing entry related to the new user and the new item, right? But then now what can we do? So the one natural way to address this challenge is to use some other information like side information. So for example, we may want to use a social network like a Facebook social graph to infer the taste of the new user, or we may want to use the graph, so-called item similarity graph, which capture the similarity across item if that is available, right? And in fact, many people took this approach to try to address this challenge, and these are their effort. And many people come up with many algorithms in many contexts, actually. And from that, actually, they could show that the such side information can help a lot indeed, actually. But here, there's one missing point. The one missing point is that there is no theory here, and meaning that they could only show that such side information can help a lot, but they could not figure out the maximum gain that we can get due to side information. So this is a problem. So this is exactly where our contribution lies in. So in this work, we could characterize the maximal gain due to side information under a simple setting. Okay, then now let me explain what that simple setting that we focused on is. Okay, here is that simple setting. So we consider the case where we have n users and m items. And the rating is very simple. It's just a like or dislike. It's just a binary rating, 1 or 0. Okay? And as a side information here, we assume that we are given only one-sided graph, like, for example, the social graph information. This is side information that we assume. And about this social graph, we are making 3 assumptions. One is that, just for simplicity, we consider the case where only there are 2 clusters. Okay? And also, we are assuming that each cluster has exactly the same rating over item. So here, then, we have only 2 vectors. Let's say V1 for the blue cluster and the V2 for the red cluster. And then, so here you can see that this setting is 2-bit simple, right? And there's a reason as to why I consider this kind of very simple setting. The reason is that it turns out, even in this very simple setting, the quantification of the side information gain is not that simple. That's why we consider this setting as just an initial effort. Okay, so this is the second assumption. And the third assumption is about this graph, social graph. So here we assume that this social graph follows a standard graph model, which is SBM. In the SBM, there are 2 parameters, alpha. Alpha indicates the intra-cluster edge probability, and beta is about the cross one. Okay? Then under this setting, the task we are interested in is the following. So the 2 information are given here. One is the partial metric that I call, And here specifically we assume that each entry is observed independently with probability p and is possibly flipped by noise with probability, say, theta. Okay? And the second information is a social graph as per SBM. Now, given these two, the task is to recover metrics. So specifically in this work, the goal is to characterize the minimum number of the observed entry required for the reliable metrics completion, meaning that we are focusing on characterizing the minimal sample complexity. So in this work, we could characterize this one. Here's the main result. So to remember that in this work, we wanted to quantify the gain of using site information, right? So for that, to see that one actually, I'm going to present the sample complexity result as a function of the amount of information that can be offered by the social graph. Then you may wonder how can you quantify the amount of information in social graph? So here is my choice, okay? So remember that we consider which model? SBM model, right? In the SBM model, we have a two-parameter alpha and beta. Here, the one key observation is that here, this distance is what? So here you can see that if this kind of a distance, alpha, square root of alpha minus square root of beta is bigger, that means what? It is easier to classify, right? Easier to classify, right? Then we can view this kind of distance as a kind of a quality of the graph. So the meaning that we can view this as kind of the amount of information that can be extracted from the social graph. So this motivates us to adopt this as the amount of information in social graph. So I denote this by simply IS, information of social graph, IS. Okay, so here just for illustrative simplicity, here we're going to consider a very simple setting where the metric size is of the following, is n is equal to 2m. The number of the user is twice number of the items. And also we just first focus on the setting of where there's no noise, okay? And of course we have some general result for the arbitrary NNM and the noisy setting, and I'm going to present that one later on. So here if IS is equal to 0, then here it turns out we can obtain the pure matrix completion result. So in this case, it turns out the sample complexity is 2 times n times log n. Now, if we increase IS, then what happens? The situation is getting better and better, right? Then we can do better and better. Then sample complexity should go down. And it turns out we could get the following curve like this. It goes down, but if IS is beyond this number, then it's saturated. So then why saturated here? Why not going to 0, right? So then here, if you think about it, then it makes sense because here the exact clustering does not guarantee, does not ensure the recovery of the rating vector, right? So that in order to do the matrix completion, we also need to estimate the rating vector as well on top of the exact clustering, right? But exact clustering does not guarantee the recovery of the rating vector. That's the reason. So we need to have at least this number of the observation, actually. It turns out that is n times log n over n. So then here by comparing these two, we can see that the gain is almost double. But remember that this is a case where the n is equal to 2m. Now the question is that what about for the general n and m case? It turns out that if the matrix is highly tall, then the gain is much more significant. So to see that one, actually, let's consider one such setting where the n is equal to m squared. So in this case, it turns out the slope is much steeper, and here the saturating point is now the square root of n times log n over 2. So here you can see that the gain is now the order-wise. Okay? So then now, as I mentioned before, that we have some general result for the arbitrary n and m and the noisy case. And here is that general result. Here you can see that some noise effect reflected in the theta here. And also we have some terms including m. So this is the general result, and this is information theoretic limit. So this is just a sharp threshold. Okay, this is one contribution. And in this work, we have another contribution. And we could also develop the computationally efficient, nearly linear time algorithm that can achieve this limit, but for a regime where this IS, information of the social graph, is order-wise greater than 1 over n. Actually, this is a regime where only the weak recovery of the clustering is possible. Okay, so now then for the rest of the talk, I'm going to explain how our algorithm works for this regime only. Okay, that's the outline. Okay, let's move on. Our algorithm actually inspired by the recent development that I'm going to tell you soon. And in fact, matrix completion and the clustering are the NP hard problem and the highly non-convex. So this is a very hard problem in general, of course. However, a recent effort has been made to address this challenging problem. That is to take a two-stage approach where we first obtain an initial estimate using some reasonably good performing algorithm like a spectral method. And then we do the local refinement in the next stage. And it turns out that this two-stage algorithm can offer a very good performance in many applications like phase retrieval and community detection or the robust PCA and EM and ranking and many others applications. So inspired by this, we took this approach, of course, to show that this is the case for our problem setting as well, but with some additional steps. So here's a detail of our algorithm. So in our algorithm, we have additional steps. So our algorithm now consists of the 3 stages. So first stage is about clustering. We first start with the clustering. There's a reason why. So remember that here our efficient algorithm focus on the regime where the IS is orderwise greater than or equal to 1 over n, right? As I mentioned before, this is a regime where the weak recovery is possible. So then this allows me to do something about the clustering, right? So that's why in the first stage, we apply some clustering algorithm like a spectral clustering to obtain an initial estimate. That's what we do in the first stage. Here the xi denotes the user i's cluster type. And here what I mean by the weak recovery is that the average error and reflected in the average L1 norm error goes to 0 as n goes to infinity. That's what I mean by the weak recovery. And based on this, now we want to estimate the 2 rating vector, V1 for the blue cluster and the V2 vector for the red cluster. And that's what we do in the next stage, stage number 2. In stage number 2, so in order to estimate the rating vector, here we just apply a simple majority voting rule. And here's how it works. And here, based on this clustering information, we first aggregate all the rating information of the users that belongs to the same cluster, for example, the blue cluster. Okay? And then by using the rating information in that blue cluster user estimated, together with the majority voting rule, we estimate the rating vector for the blue cluster, which is, I call, V1. And here's the detail how we obtain the V1. So for example, for item number 1, we just look at all the available rating. Here we have a 2, 0, and no 1. Then we declare it as, of course, 0. And for item number 2, here we have a 2 1s and 0, 1, 0. Then we declare it as, what? 1, of course. And for the third item, we declare it as 1 and all the way down to the last. Okay, this is how we estimate V1. And similarly, we also estimate V2 in a similar manner. And this is how we estimate V1 and V2. And it turns out we could show that if IS is orderwise greater than 1 over n, that's the case where the weak recovery is possible. Then, if the sample size is also the fundamental limit that I claimed earlier, then we can ensure the exact recovery of the 2 rating vector V1 and V2. That's what we show. Okay? And now, are we done? Of course not. Yeah, because I told you that there is another stage, third stage. So here there's a problem. The problem is that this estimating the recovery of the V1 and V2 is not sufficient to do matrix completion, because matrix completion also requires a knowledge of the exact clustering. But remember that in the first stage, we only guarantee the weak recovery, not the exact recovery, right, of the clustering, right? So this motivates us to employ the third stage, where the goal is to make sure the exact clustering. So here, to make sure the exact clustering, the idea is to use the point-wise maximum likelihood estimation. So here's how it works. So for example, here, in order to estimate ith component of the cluster type, and we compute two things. One is a likelihood function with respect to these two observations conditioned on the initial estimate, initial ith estimate. Okay, this is what we compute in the first place. And the second thing that we compute is a likelihood function with respect to the observation given its now flip version, xi plus 1. And then if this guy is greater than this one, then we keep the initial estimate. And otherwise, we take the flip version. Okay, this is how it works. And we do this for all items, and one by one, and step by step. And this forms a one iteration. Okay? And it turns out what we have shown here is that if is is autowise greater than 1 over n, and the sample size is above the fundamental limit that I claimed earlier, then with one iteration, we can improve the error rate by a factor of 2. That's what we show. Then this suggests what? With now around the log n iteration, we can ensure the exact clustering, right? Because one iteration, we can improve the error by a factor of 2. Now then with the log n iteration, we can guarantee the exact clustering. This is how we prove the achievability. Question?
What does an iteration consist of? What happens in an iteration?
Okay, here is a one iteration. So in the first iteration, we apply this rule for all items. We encompass all the items. We did all the operations for all items. Then that forms a one iteration. And it turns out with one iteration, we can improve the error rate by a factor of 2. That suggests that with the log n iteration, we can ensure the exact clustering. That's how we prove the achievability of this algorithm. Is that clear? Good. And we also show the optimality of this algorithm using some bounding technique like union bounds and the Changho bound and something like that. Okay, so, and finally, let me say a few words about the related work. Actually, my friend, Arya Mazumdar, and his wife considered a similar problem, where the task is to recover now the clustering using matrix rating as a side information. So then now here you can see that now the task is now flipped. Then here you can see some similarity, but here I'd like to emphasize one key distinction. So one key distinction is the following. Here in this problem, exact clustering does not ensure, does not guarantee the recovery of the rating vector, right? But on the other hand, in our problem setting, the matrix completion also guarantees the exact clustering. So the meaning that the exact clustering comes as by just a consequence of the matrix completion. So in that regard, these problems are different. Okay, now let me conclude. So in this work, we could characterize the minimal sample complexity of a matrix completion problem with the social graph information under a simple setting. And from this, we could characterize the maximal gain due to side information. And we could also develop a computational efficient algorithm that can achieve the limit. And here, the one thing that I'd like to mention about the future work is the following. So here, in this work, the setting that we consider, as I mentioned before, is a bit simple, right? So the one natural feature work is to extend this to a more general setting. For example, the constraint of the equal rating vector is now more relaxed. Or you may want to have a two-sided graph information instead of a one-sided one. Or the ratings are beyond binary, something like that. Okay.
Let's thank the speaker. Questions? I will start then. So thanks for the talk, very interesting talk. Have you looked into how much structure can you allow into the sampling as a result of adding the side information? So can you tolerate samplings that go into Markovian sampling or something that is not IID basically?
Oh, that's a good question. So here I just consider the passive setting, right? Where the samples are just random, right? Mm-hmm. But maybe someone may want to go forward to consider the active sampling, right? Mm-hmm. Which allows some correlation across sample, right? Mm-hmm. That's a kind of a good setting, but it turns out that's a very hard problem. So you first consider this setting, but As of now, I have no idea as to how to attack that problem, actually. So,
All right.
in general, the active sampling problem is not that quite easy, right?
So in the examples you showed, there was a number of users bigger than the number of items, right?
That's right, that's right.
Oh, so does this threshold behavior still appear when it's the other way around? Because that's more typical, right?
So it turns out, so if you consider the one-sided graph where we have a social graph, then we have a gain only when n, number of user, is greater than the number of items.
I see.
If that's not the case, then there's no gain. So here's my suggestion. If we have that case where the m is greater than m, then I suggest to use the item similarity graph. So meaning that the other way around the graph, actually. So that way we can gain, we can get some gain.
I see.
So my suggestion is to use a two-sided graph if that is available. That may be the best.
Any other questions?
Pong?
Comment on what is the technical difficulty when you relax the condition of the rating vectors being binary or equal? Like if you had Gaussian, let's say that within the same cluster it's just mu1 plus some Gaussian noise. Right? So in analyzing your upper bound, what was the main technical problem?
Oh, so in analyzing the bounds, we don't have any difficulty actually. So that we can relax that one. The problem is that in reality, we don't know which model is good. That's my problem actually. Here, we just considered a very simple setting where all the rating vector are the same across the user in the same cluster, right? That's only for the simplicity. But in reality, that's not the case, I guess. But we don't know with which model we can capture that one actually. But there's no technical difficulty. Actually here, in the second stage, we just apply the majority voting rule, right? That's because we consider a very simple setting. But that's the stage that we need to perturb if we consider a more complicated setting. Do I answer to you? Good.
Any other question? So I have another question actually. I was wondering if you move beyond graphs that you build stochastically, right? Is there any sort of notion of coherence between the graph and the sampling in the same way that there is the notion of coherence between the basis, right, for the matrix and the sampling that governs how much you can gain from the graph information? Have you looked into anything that moves beyond just the stochastic setting?
Oh, here I just focus on the SPM model actually,
Yeah.
so I did not consider the other model.
Okay.
I have no idea about that.
All right. Okay. Another quick question.
So for your algorithm, you don't need to know the alpha and beta, right? Or do you need to know what they are?
Oh, that's a very good question. So in the third stage, actually, we employ the point-wise MLE. So that requires knowledge of three things, actually. One is alpha, and second one is a beta and theta as well.
Okay.
So my suggestion is to estimate those quantity in the first place, and then apply the third stage algorithm.
I see. Thank you.
So that's what I did in our real implementation of the algorithm. Okay, thank you for asking that one question.
All right. Let's thank the speaker.